So this unit, we've been talking about patterns and relations, okay? And we talked about the first lesson, we talked about a way to show the relationship between two variables using a scatter plot, okay? Now what we want to look at is we want to analyze, and we did this somewhat, what kind of relationship forms between two variables. And usually it can come down to linear, nonlinear, or just random, okay? And I mean, we want to know the answer to these things. Like, so for example, you want to determine if the price of a laptop increases at the same rate as the amount of memory. You know, do they increase at the same rate? Does, does the cost increase exponentially, like at a curved rate compared to if you have more memory? You know, get us an idea of what we can afford. So let's look at the different types of patterns we can see when we graph a series of points. Okay. So here we've got three situations. The first one, like, how would you describe A? How would you describe the points in A? It would be random, because they just seem to be. So we could say no pattern. Points seem to be random. Okay. How would you describe B? Yeah. Okay. This would be linear, even though the points don't form a straight line, like an exact straight line. It's close. So that's one thing we've got to sort of establish when we look at a series of points on a graph. It doesn't have to form a straight line to be linear. If it's kind of heading in one direction up or one direction down, and it looks like you could draw a line through it, like, and maybe get half the points above and half the points below, then we could call it linear. But how about this one? Well, it's an inverse relationship, you're right. As one goes up, the other comes down. Would you call it linear? No, we would say this is nonlinear. It's more of a curved pattern, okay? Not a straight line, but a curved pattern. So there's still actually a pattern going on, it's just not linear. Compared to the first one where there's just nothing going on. Okay? Tell me which ones are which. Would you say A? What's that? It's, I mean, there's a few points that come off it, but I could make a pretty close straight line. So we would probably call this linear. How about this one? Yeah, but it does have a kind of a pattern to it. So we wouldn't say no pattern, we'd say nonlinear, because it's almost like a bell-shaped curve. See? What's that? Yeah, no pattern. And D? Linear. We're going to focus on the linear. And we're going to look at various examples in real life that form linear relationships, or we can make it into a linear relationship. So what's a linear relationship or a linear relation? Well, if we plot it on the graph, it looks as though a straight line could be drawn through it. Okay, not drawn, and that does not mean, and that's really important to note. Okay, the data does not have to go through every single point. If it just looks like everything's going up in one direction or looks like it's coming down, we can call it linear, as long as it doesn't curve as well. There's going to be some relationships that are perfectly linear. As one goes up, the other goes up the same amount. Okay? There's going to be some that are very close to linear. As one goes up, the other goes up, maybe not necessarily the same amount. But what we do with data like that is we put in something called the line of best fit. And we'll see that in a second. Okay? So we're first going to start with the scatter plot. See if it's linear. And if it's linear, how could we draw a line that sort of represents the data? A straight line. So we did scatter plots in the last lesson. So we're going to do this one, put it on a scatter plot. Okay. And then we're going to see, and then we'll see it doesn't form a perfect line, but we're going to try and put a line of best fit in it. First column is the independent or horizontal axis. Where should I start? Remember, we can use the squiggly thing at the beginning. We always start at 0, but we can use the squiggly thing to skip some grids. Where do you think we should start, and how much should we go up by? What's the lowest value? All right, so why don't we start at 60? What's the highest value? So it looks like maybe we can go up by 2s. Couldn't go up by 1s because that's too many. So why don't we here do our, oh, it's not going to work. Do our little squiggly thing. Oh, come on. Yeah. And we'll start at 60. And then we'll go 62, 64, 66, 68, 70, 72, and 73 was the highest, so I only have to go to 74. And that represents the height. We want to label, and that's in inches. For the weight, we don't want to start at 0 because then there's too many to plot. So we look at the lowest value, which is what, 110? And the highest value is 200. So we want to do a little squiggly here and maybe start at 100 and go up by 20s. I think if we went up by 10s, we wouldn't have enough to get to 200. So let's start at 100 and go 120, 140, 160, 180, and 200. And that's the weight. Don't forget the title. So we could just call this.
Is that 168 or 1?
Oh, sorry. Yeah. 160. Oh, I did it again. 160. Height and weight of male students. Okay. And now let's plot. 61, 110. Right there. Put a little X. 69, 150 up here. 71, 180 up here. 62, 120 right at the intersection there. 65, 140 on that line there. 73, 200, that's the highest one. 65, 130, that would go about there. 72, 165, that's 170, so somewhere around there. And 70, 180. Should look something like that when you plot it. Would you consider this linear? First of all, would you consider it random? No, it wouldn't be random. Would you think that there's any kind of curve to this? No, it doesn't look like the points are curving up or curving down. So that really leaves us with linear, but you can't draw a line through every single point, can you? But we could draw a line that best represents the data with basically half of the points above and half of the points below. Yeah. Height and weight of male students. Height and weight of male students. So the question is, how would you draw it? And this is a bit of a judgment call. Okay? Like, I want to draw a line of best fit. Like I said, about half of the points will be above, about half of the points will be below. So would it make sense to draw a line there? No, because everything's above. Wouldn't make sense to draw a line here because everything's below. We want it to sort of cut through most of the data. So maybe something like that. Is yours going to be exactly the same as mine? No, it might be slightly off, but you'll be close. So you can see that we have like 4 X's above here, 3 X's below here, and 1 X right on there. It doesn't have to have the same number above and below. But that's a pretty good representation. So that's our line of best fit. And why do we do a line of best fit? Because then it allows us to make some predictions. Because then I could say, okay, what would be the weight of a student that has a height of 74 inches? Well, according to my line of best fit, if I go up to 74 inches, I'm hitting about 190 pounds. Okay? Is it going to be like if we find a male student who's 74 inches, are they going to be exactly 190? No. But they'll probably be close to it. Unless they're freakishly small or freakishly tall. Freakishly short or freakishly tall. Gives us an idea. Like even though in our data, the 73 one was up to 200 and we're saying the 74 one is up to 190. Remember, that's based on all the data, not just one. And we're going to just sort of leave it like that. Okay? I mean, we use statistics that we can calculate an exact line of best fit, but that's beyond this course. Okay? We can use a rough line of best fit and kind of eyeball it. Okay. Everybody done with this? So on a graph, we can see whether a set of points are linear, nonlinear, or have no pattern at all. Okay. What about if we've got a set of numbers? Because we can tell whether a set of numbers is linear, nonlinear, or no pattern. We just use different words. So for example, let's say you're given these four numbers, 2, 4, 8, 16. What are the next two? According to this, it seems like we've got a pattern going on. What kind of pattern? Depends. What would the next two be? 32 and 64. How did you get that? Yeah. Each term is double or 2 times the previous term. Whenever we multiply to get to the next term, that's an example of a geometric sequence, something that we're actually not going to look at, but some of you have seen before. We've dealt with them in grade 11 now. Okay. We get each term by multiplying the previous term by the same number. Whenever we graph these things, and we can graph sequences of numbers, it will always be curved, which is not what we're focusing on in this unit. Okay. What we are going to focus on is arithmetic sequences. Or linear patterns. That means we get each term by adding the previous term by the same number. And that number, whatever we add, it could be positive or negative. We could keep adding a negative number to a group, which is really just the same as subtracting. So let's look at these ones. So you got to see, are you adding the same amount every time? Positive or negative? If you are, it's linear. If you aren't, it's not, and we don't do anything with it. If it is linear, you need to say, what are we adding by each time? Is the first one linear? Are we adding the same amount every time? Yeah. What are we adding every time? 8. So it's linear. How about B? Are we adding, remember you can add a positive or negative. So to get from 32 to 16, yeah, you can say subtract 16, or you can say add negative 16. Well, this one, from 32 to 16, we add negative 16. From 16 to 8, we add negative 8. We're not adding the same number. So it's not linear. How about C? Well, we're going down by 1 each time, or adding negative 1 for the first couple, but then we're going back up, aren't we? So we're going down by 1 a couple of times, and then we're going up by 1. That's not linear. And for D, we're going down. The question is, are we going down by the same amount every time? How much do I go down by to get from 114 to 101? 13. So yeah, so I'm adding negative 13. And that happens, 101, negative 13 gives me 88, negative 13 gives me 65, which gives me 62. So that one's linear, and it goes down by I should say, I know it sounds weird, it goes up by negative 13, or we add negative 13. I should say we add negative 13, not it goes up by negative 13. It's too confusing. Okay, so we've seen how a series of numbers can be linear or nonlinear or random. We've seen how graphs can be linear, nonlinear, or random. Another way we can show a relationship, and we often use this before we graph, is a table. Okay? So how do we tell if a table's linear? Well, we could graph it and look at it. But without graphing it, can we see whether it's linear or not? Well, let's look at, there's a couple ways you can look at patterns here. So here we have, you purchase a certain number of apples, and depending on how many you purchase, you get free apples. So if you purchase 5, you get 1. If you purchase 10, you get 2. Purchase 15, you get 3. I want to know if this is linear. Okay. So how do we do this? Well, let's look at what's happening in each row. How much am I going up by? in the top column by 5. So it's 5, 5, 5, 5. How much am I going up by in the bottom column or the free apples column? 1. If each one of them, okay, so the number of apples purchased goes up by 5, the number of free apples goes up by 1. So if we look at each one, they're going up by the same amount. They don't have to be they don't have to be identical to each other. It's just in this row, they're going up by the same amount, 5. In this row, they're going up by the same amount, 1, which means we can say that it's linear. Because for every 5 apples we purchase, we get one free one. We could write that using words. Like not only do we see a pattern going this way, there's also a pattern going in each pair. What math am I doing to this to get this each time? To get from 5 to 1, to get from 10 to 2, to get from 15 to 3. What am I doing each time? I'm dividing by 5. That's another way you could express the relationship. Okay? So we could say the number of apples divided by 5 equals the number of free apples. So that way you could figure out, I mean, this is actually more efficient. This is a pattern we want to know more, because then we can answer more questions from it. Like, because if I said, you know, how many free apples would you get if you bought 45 apples? Well, you could keep counting up until you get 45, but that's not very efficient. All I have to do is take 45, divide by 5, and know that I get 9 free ones. Sometimes it may not be as clean as this when you see a table. For example, here. Here's another relationship shown in a table. You got the number of floors in an apartment building, and you got the number of apartments in that building. Well, what's happening here? Well, we go up by 1, up by 1, up by 1, but then up by 4. And then in this one, we go up by 12, up by 12, up by 12, but then up by 48. Oops. So for the first 3, it looks linear. If I didn't have this one, I could definitely say it's linear. But because of that last one, it's a little bit confusing. So how do we deal with that? We find the rate of change that each one is changing at. So I take pairs of data, this pair, this pair, this pair, and this pair, and find the rate of change. How do I find the rate of change? This is something we did in grade 10 pre-calculus. It's the difference between the dependent variables, or the bottom ones, over the difference in the independent variables. Okay? So for this example, I would want to find 4 rates of change. the rate of change, this pair, then this pair, then this pair, then this pair. If they're all the same, it's linear. So I'm going to use several different colors here. So the rate of change of this pair, it's the difference in the dependent variables, so 48 minus 36, over the difference in the number, or in the independent variable, 4 minus 3. So take the second one minus the first over the second one minus the first. And what do we get? 12 over 1, which is 12. This pair. Take the second bottom one, 60 minus 48, over the second top one minus the first. Again, we get 12 over 1, which is 12. So it's the same rate of change. As soon as it's different, we stop because it's no longer linear. That one. Second dependent minus first dependent, so 72 minus 60, over second independent minus first independent, 6 minus 5, gives me 12 over 1, which is 12 again. Which makes sense, actually, that these are all the same, because we saw that the first part was linear. It's this last pair that I got to wonder about, because the top jumped by 4 and the bottom jumped by 48. So which color should I use? Yellow? Would you be able to see that? Yeah. So we do that one. So second dependent, 120 minus first dependent, 72, over 10 minus 6 gives me 48 over 4, which is 12. It's the same rate of change, okay? Even though the numbers jumped from 4 to 4 and then 48, the proportion of the jump stayed the same, which is what the rate of change measures. So if they're all the same, it's linear. Like I said, as soon as one of them changes, it's no longer linear. Let's try one more. Table of values shows the relationship between the number of gigabytes of memory for some machine and the cost of the machine. Does it represent linear? Well, this is, first of all, this is not going up by the same amount each time, and neither is this. So we can't just use the table. Okay? We're going to have to use the rates of change. And remember, as soon as one of them becomes different, we stop. So what's the rate of change of the first pair? It's the second dependent minus the first dependent over the second independent minus the first independent, which gives me 20 over 1, which gives me 20. So that's a rate of change of 20, or in other words, as the independent increases by 1, the dependent increases by 20. Next pair. Rate of change of this is the second dependent 100 minus the first 40 over the second independent 8 minus the first 2. And that gives us 60 over 6, which is 10. That's a different rate of change, which no longer makes it linear. So I can stop. I don't have to go any further because it doesn't matter. It is not linear. Okay.